Now have a look at the next question, dear students. White light is used to illuminate the two slits in Young's double slit experiment. The distance between the slits is B and the screen is at a distance D, which is far greater than B from the slits. At the point on the screen directly in front of one of the slits, certain wavelengths are missing. Some of the missing wavelengths are options A. Lambda is equal to B square by 2D. B. Lambda is equal to 2B square by D. C. Lambda is equal to B square by 3D. And D. Lambda is equal to 2B square by 3D. Okay, dear students, let's first have a look at the experimental apparatus for YDS experiment. Now, let P be that point which is directly in front of one of the slits, that is S1. And here you should be aware of the symbols that they have used in the problem. That is, the distance between the slits and the screen is given by the symbol small d, and the separation between the two slits is given by the symbol b, small b. So now if this is B, then the distance between O and P on the screen should be half of B, that is B by 2. The question asked here is, there are few wavelengths missing at point P. Remember, we have made use of white light here, and the missing wavelengths corresponds to the minimum or the dark fringe at point P. So you'll have to write a condition for minimum at P or the dark fringe at P. So what do we know about P? At P, the distance from the center, that is X, is given to be B by 2, that is half of B. And you know that a minimum is formed at P. Therefore, we'll write the condition for minimum, or the dark fringe is formed. And what do you know about that dark fringe? You know the distance of the fringe. So let me make use of the distance of dark fringe. We have an expression for distance of nth dark fringe from the center is given by xn is equal to 2n plus 1 lambda d divided by 2d is the expression. And let me make use of the real symbols which are given in the question, that is 2n plus 1 into lambda into, in place of capital D you should write small d, divided by 2 into, in place of small d you should write small b. This is equal to the distance of the dark as given in the figure. It should be equal to b by 2. Now you can cancel this 2 over here, and you can find out what are the missing wavelengths. So we are supposed to find out expressions for lambda here. So lambda is equal to cross multiplication gives you b square divided by 2n plus 1 times d. Remember, here n is the order of the fringe, which always takes values starting from 0. So the possible values of n are 0, 1, 2, 3, so on. Now keep on substituting different values for n, you'll get different possible values of wavelength. So we'll have to have a look at different options given for us by substituting different values for n. Put n is equal to 0. If n is equal to 0, you'll get lambda is equal to b square divided by t. If n is equal to 1, you'll get lambda is equal to b square divided by 3d. If n is equal to 2, you'll get lambda is equal to b square divided by 5d and so on. So out of these, I think there is one option given which is b square divided by 3d. Therefore, option C, b square divided by 3d is the correct answer. Now look at the next question, dear students. In a double slit experiment, the angular width of a fringe is found to be 0.2 degree on a screen 1 meter away. The wavelength of light used is 6000 angstrom. What will be the angular width of a fringe if the entire experimental arrangement is immersed in water? Refractive index of water is 4/3. Options: A 0.15 degree, B 0.18 degree, C 0.2 degree, and D 0.27 degree. Students, this is a question based on angular width. Let's first of all understand what is angular width of a fringe. Now, if you consider the experimental apparatus, now if I say that this is the width of one fringe, that is beta, then the angular position of this fringe, let it be denoted by some theta. The separation between the slits and the screen is given to be capital D. So if this is the case, that is when beta is the linear width of the fringe, then you can always define what is called as the angular width of the fringe. That is theta is equal to beta divided by D. Of course it is tan theta, and for small angles tan can be ignored, or I can write this as simply equal to theta. And if it is beta by D, using the expression for beta is equal to lambda D by D, you can write this beta by capital D as equal to lambda by small d. Therefore, the angular width of a fringe is theta is equal to lambda divided by small d. So from this it is clearly evident that the angular width of a fringe depends directly on the wavelength of the light used. That is, theta is directly proportional to wavelength. And further we know that wavelength of light depends inversely on the refractive index of the medium. So from these two you can conclude that the angular width of a fringe is inversely proportional to the refractive index of the medium. So in other words, you can write this as n1 theta 1 is equal to n2 theta 2 since their product remains constant. Now, when you are given with the datas of the angular width in two different media of different refractive indices, then you can make use of this formula. That is, here n1 is in air whose refractive index is 1, and theta 1 is the angular width in air which is given to be 0.2 degree. That should be equal to n2, the refractive index of the second medium, that is water, whose refractive index is 4/3, into theta 2 is the angular width in the water medium which is unknown. Let me call it as theta. Therefore theta is equal to 0.2 into 3/4, that is 0.6/4, that should be 0.15 in degree. Therefore your option A should be the correct answer. However, there is a shortcut for this. Whenever there is a change in width, change in linear width, or change in angular width is asked when the entire apparatus is immersed in water, I think you can go for a shortcut. The shortcut is, if beta air or beta A is the fringe width in air and beta W is the fringe width in water, similarly, if theta A is the angular width in air and theta w is the angular width of the fringe in water, you can connect a relation between beta air and beta water by beta water is equal to beta air divided by the refractive index. Similarly, theta water is equal to theta air divided by refractive index. Remember, dear students, refractive index can also be expressed as the ratio of beta air by beta water, and it has to be beta air by beta water and never beta water by beta air, because refractive index should always be greater than 1 and beta will be maximum in air medium. Therefore, beta air is always greater than beta water. Therefore, the ratio of beta air to beta water should always be greater than 1. Therefore, refractive index can be given by the expression beta air by beta water or theta air by theta water. Let me write that expression also. Theta air by theta water will also give you the expression for refractive index. So when you substitute for theta air by refractive index, again you'll get the same expression, that is 0.2 divided by 4 by 3, that is 0.15 degree. Therefore option A is the correct answer. Now have a look at the next question, dear students. In an interference experiment, third bright fringe is obtained at a point on the screen with light of wavelength 700 nanometer. What should be the wavelength of light source in order to obtain fifth bright fringe at the same point? Options: A 500 nanometer, B 630 nanometer, C 750 nanometer, and D 420 nanometer. So here it's the problem based on the superposition or the coincidence of the fringes. Two bright fringes coincide when the distance between them from the center is equal. That is, when two different fringes coincide, when two bright fringes coincide at a point on the screen, then the distance of these two fringes from the center will be the same. So when you have the same distance, you can make use of the distance formula. The distance of bright fringe, I'll make use of this formula. The distance of bright from the center is given by xn is equal to n lambda d divided by d. So for two different fringes, when they coincide, this x should be same. However, the number of fringes, that is the order of the fringe n and the wavelength lambda, will be different, and capital D and small d will remain the same for the same experimental apparatus. Let's have a look at the data here. N1 is equal to 3 for a wavelength lambda 1 is equal to 700 nanometer. And fifth bright fringe, that is N2 is equal to 5 for the unknown wavelength which is to be found out. So here it clearly says that the third bright fringe due to 700 nanometer coincides with fifth bright fringe due to the unknown wavelength. So let's equate their distances. That is, let me say that x1 is equal to x2. When I equate these two distances, in place of x1 you can write n1 lambda 1 d by d. That should be equal to n2 lambda 2 into d by d. Here please note a fact that capital D and small d remain the same since the experimental apparatus is unchanged. Therefore, when you cancel these, you're left with the expression, that is n1 lambda 1 is equal to n2 lambda 2. So dear students, make a note here that you can make use of this expression directly, that is n1 lambda 1 is equal to n2 lambda 2 when two bright fringes coincide at a point. Now let me substitute for these values to find out lambda 2. Let me write down expression for lambda 2 first, which is n1 by n2 into lambda 1. n1 is 3, n2 is 5, lambda 1 is 700 nanometer. So this is 2100 by 5 should be equal to 420 nanometer. So the unknown wavelength is 420 nanometer. Therefore, option D is the correct answer. Now let's work out one more question on the coincidence of the fringes, dear students. A mixture of light consisting of wavelength 590 nanometer and an unknown wavelength illuminates Young's double slit and gives rise to two overlapping interference patterns on the screen. The central maximum of both the lights coincide. Further, it is observed that the third bright fringe of known light coincides with the fourth bright fringe of the unknown light. From this data, the wavelength of unknown light is options A 393.4 nanometer, B 885.0 nanometer, C 442.5 nanometer, and D 776.8 nanometer. Right, this is again a problem on coincidence of the fringes. Here lambda 1 is given to be 590 nanometer. Lambda 2 is unknown, which I'll write as just lambda. N1 is 3 and N2 is 4. That is, third bright fringe due to 590 nanometer coincides with fourth bright fringe due to unknown light. And for bright coinciding with bright, we have an expression which can be used as a shortcut as N1 lambda 1 is equal to N2 lambda 2. Dear students, make a note here that when bright coincides with bright, you can make use of this formula. N1 lambda 1 is equal to N2 lambda 2. When dark coincides with dark, you can make use of the expression which I'll write here as 2n1 plus 1 into lambda 1 by 2 is equal to 2n2 plus 1 into lambda 2 divided by 2. However, you can cancel these 2's. So you're left with the expression 2n1 plus 1 into lambda 1 is equal to 2n2 plus 1 into lambda 2. So when bright coincides with dark, you can make use of the expression n1 lambda 1 is equal to 2n plus 1, here it is n2, 2n2 plus 1 into lambda 2. So depending upon the conditions maintained, the conditions given in the question, you will have to change the formula. So when bright coincides with bright, stick on to the formula n1 lambda 1 is equal to n2 lambda 2. And you know that this is the formula extracted by equating the distances of those two respective bright fringes. Now let us rearrange this expression to get an expression for lambda 2. That is equal to n1 by n2 into lambda 1. So it is 3 by 4 into 590. 590 is slightly less than 600. Therefore, you can approximately write it as 600 by 4 is approximately 150. Therefore, this should be less than 150 into 3. So 150 into 3 is 450. Therefore, this answer should be slightly less than 450. I think there is only one option which is very close to 450, that is 442.5 in nanometer. That is your option C. Therefore, option C is the correct answer. 442.5 nanometer is the wavelength of unknown light. Now look at the next question, dear students. 4 independent waves are represented by equations. 1. x1 is equal to a1 sine omega t. 2. x2 is equal to a1 sine 2 omega t. 3. x3 is equal to a1 sine omega 1 t. 4. x4 is equal to a1 sine omega t plus delta. Interference is possible between waves represented by equations. Options: A 3 and 4, B 1 and 2, C 2 and 3, and D 1 and 4. Dear students, we know that interference is possible when the two sources are coherent. That is the main condition for the sustained interference pattern. In order to achieve well-sustained interference pattern, the two sources should be coherent. and the condition for coherent is that the phase difference between the two interfering waves should be constant. So look at the given 4 different equations and you can find that there is a constant phase difference is maintained between 1 and 4. You have a look at equation 1, that is x1 is equal to a1 sine omega t and x4 is equal to a1 sine omega t plus delta. Have a look at these two equations. They are maintained with the same amplitude, that is amplitude between these, that is the amplitude of these two waves is the same, which is not a necessary condition to obtain well-sustained interference pattern. However, the phase difference between these two is delta, that is a must condition. Along with this, one more important advantage is that look at the frequency of the two individual waves. That is the angular frequency is omega and omega, which means that the two sources have got same frequency. The frequency of them is omega, which is same for the two sources. Therefore, you can say that the two sources are coherent sources and interference is possible. That is 1 and 4 can produce interference pattern. Therefore, that is the correct answer, which is given in option D. Therefore, option D is the correct answer.